Alarms are already screaming. Pressure doors slam shut one after another. In habitat Ring A, someone is shouting for oxygen masks. 7 minutes before local sunrise. A buried valve has turned their oxygen into a bomb. And right now, in the service trench below them, the fire has already started. The base's telemetry officer sees it first. Oxygen demand spikes. Then power draw in the life support cluster surges off the chart. He knows what that combination means. Hidden somewhere in the structure, there is a leak. Leak plus electrical load plus confined space. In a normal building, you get a fire. In a lunar base built from pressurized cans sitting on vacuum, you get shrapnel. If the crew can't find and isolate the leak in 6 minutes, the oxygen tanks below Ring A will explode. When they rupture, they will rip open the habitat above. 8 people live there. There are only 2 escape rovers. The mission dies with them, and the program that put humans back on the moon might never recover. Tonight, we're going to follow exactly how one frozen valve turned lunar dawn into a countdown to destruction. Let's rewind. The base sits inside a shallow crater near the South Pole. Engineers chose this spot for one reason. Sunlight kisses the crater rim almost all month long, but the floor where the base lives stays cold and dark. Above ground, pressurized modules, labs, sleeping quarters. Below ground, the dangerous stuff. 4 liquid oxygen tanks, water recycling, power and data conduits. To save mass, engineers buried most of it in a narrow maintenance trench. Up top, astronauts get shirt sleeve comfort. Down below, temperatures swing from cryogenic to oven hot. Most of the oxygen system is kept at a stable, icy cold, but one valve is different. It sits exactly where the base shadow meets the first touch of sunrise. When the sun is down, the valve lives in perfect black sky cold. When the sun rises, its metal body is hit with raw, unfiltered sunlight. That means its outside heats fast. Its inside stays cryogenic. Over months, that thermal cycling does something subtle. Tiny cracks start to grow in the metal. Hairline fractures, too small for sensors, too small for inspection cameras. On Earth, you might see a drip, a stain, a smell. On the moon, there is no air, no rust, no water. The valve looks perfect, right up until lunar dawn. The disaster starts 6 minutes before sunrise. Inside Ring A, the crew are asleep. In the trench, a pump starts its scheduled ramp-up. It's programmed to meet the morning oxygen demand. The brittle valve does exactly what the equations predict, and what humans didn't. It snaps. High-pressure oxygen flashes into the narrow trench. In seconds, the gas concentration climbs far beyond anything survivable. The system thinks it's just meeting demand. Up above, life support units pull harder to keep partial pressure stable. More flow means more leakage. And in that trench, everything runs on high-efficiency DC power. When oxygen surrounds energized electronics, you don't need a spark. You just need a microscopic arc that would be harmless in normal air. In oxygen that pure, that arc becomes a torch. The cable insulation ignites. Flame races down the trench like a fuse. Above it, people are still sleeping. So what's really happening here? Thermal shock is simple and brutal. When one part of a metal piece heats or cools much faster than another, the hot part wants to expand. The cold part won't let it. The result is stress, invisible, internal force. Every sunrise, the valve's outer shell jumped dozens of degrees in minutes. Its core, bathed in liquid oxygen at -180 degrees Celsius, barely moved. Those thermal gradients set up repeated cycles of tension and compression. Metals can handle this, up to a point. But under lunar conditions, there are no clouds, no atmosphere. Sunlight is brutal. Shadow is absolute. The valve lived exactly on that border. Over thousands of cycles, microscopic defects grew. Engineers know this as low-cycle thermal fatigue. It's the same principle that snaps railroad tracks during heat waves, or cracks turbine blades in jet engines. Here, it cracked the one component that stood between stable oxygen flow and a trench filled with a high-pressure, pure oxygen bomb. Back in the control room, the telemetry officer finally sees something break pattern. A line contactor in the trench trips off. The system flags it as a nuisance fault. This time, he doesn't let it auto-reset. He punches the manual isolation for the oxygen pumps. Flow drops. So does pressure in the tanks, and pressure in Ring A. In the habitat, crew wake to the sound of sirens and hissing vents. One astronaut grabs her tablet and sees the trend lines. She orders a full evacuation to Ring C. Doors slam shut behind them, sealing Ring A. Below their feet, the trench fire finally finds the oxygen tanks. Without fresh flow, the gas concentration begins to drop. The fire starves. 2 minutes later, only hot metal and scorched insulation remain. The tanks never reach rupture pressure. An accident report will later call it a near loss of base incident. Afterward, investigators trace the failure back to one design choice. They had buried a cryogenic valve on the day-night border. They assumed the insulation would handle it. It almost did. Future bases will move all critical valves deep into permanent shadow, or up into sun-tracked, thermally controlled towers. They'll add sensors that measure strain inside metal, not just temperature. Because on the moon, it's not the impacts you see that kill you first. It's the quiet, repeated stresses you don't notice until they snap. On Mars, with a thicker atmosphere and dust-softened sunlight, this valve might have leaked for months before anyone noticed. On the airless moon, it almost killed a base in 7 minutes. And wherever we go next, from lunar caves to Martian canyons, the physics of metal, heat, and oxygen will follow us there. We can't negotiate with it. We can only learn faster than it fails. I am the cartographer, and this is the Atlas.